Students. So we have seen previously that neither the particle model nor the wave model was completely able to explain all of the properties of the say subatomic particle. Okay. So some properties were explainable by the particle nature while some were explainable by the wave nature. Now in order to overcome this shortcoming, so what did we do? We developed a new mechanics that is totally different from the mechanics that we know. Okay, some of the classical mechanics phenomena are of course there, but still it is very new. So that was called as quantum mechanics, right? So first of all, it was based upon the two principal theories. First was the what? First was the dual behavior of matter. Okay, that matter will behave both as a particle and a wave. And the second concept for the subatomic particles were Heisenberg uncertainty principle. Means it was basically a principle which said that the position and the momentum cannot be determined at the same time simultaneously. So we'll see all of this in more detail. So let us first start with the dual nature of matter. So de Broglie was the one who gave this wave particle duality, and he gave the equation lambda is equals to h by p to associate the wavelength of the particle with the momentum. Here p is the momentum and lambda is the wavelength. H is our Planck's constant. We know it very well. Okay. So in this way, what are we doing here? That we have the wavelength, and with each wavelength there is a momentum associated, or we could say that the reverse one is more practical, which says that if something is some subatomic particle is moving some velocity, right, then it will have some momentum, and that momentum will be what? That momentum will be lambda is equals to h by momentum. Clear? Okay. So what are the symbols here? Lambda, h, and p. So h is of course a Planck's constant, lambda is a wavelength, and p is a momentum. Okay, so this was basically this duality nature was confirmed by the part that some of these exhibit, means light sometimes exhibit diffraction and confirming that they have the wave nature. Okay, they also exhibit the interference, which is confirming that they have the wave nature. On the other hand, the electron microscope utilize the wave nature of the particle electron for high magnification. Clear? So if you talk about the derivation of this law, or you can say de Broglie law, then it is in this way. First of all, E is equals to mc square. So it is kind of building up a relation between the energy and the velocity of the particle. Second is E is equals to h nu. Of course, the Einstein hypothesis we all knew. Now next what we will do, they both are equals to energy, we will equate them both. This will give you mc square is equals to h nu. Now C is equals to nu lambda. We will just substitute that. Okay, C is equals to nu lambda. We will substitute that and we will get hc lambda is equals to mc square. Okay, or we can just substitute this nu with c lambda. So what are we done here? What are we doing here? We are substituting nu with c lambda. That would give us mc square is equal to hc lambda. Now if you find lambda here, so C will be cancelled out. What was C here? C was basically the electron. Okay, it was basically the electron. Now this C and C will be cancelled out and we will get L lambda is equals to h by c. Now here C has C is what? C is speed of light. Okay, and V is velocity. So yeah, C is speed of light and m is mass. So mass into velocity will give us momentum. So in this way your formula was formed. Clear? Okay. So lambda is equals to h by mc. This is the main formula that we know. Okay. Now if there is another any subatomic particle, then the C will change. So C is specifically for light. If you just write V here, then it can be for anything. Okay. Next. Now the wavelength associated with the ordinary object are too short to be detected. Okay. So you can see here that lambda is equals to h by mv. Okay, h by mv. Now h is a very negative value, or you can say a very small value. Now what we will do, it will be let lambda is equals to h by mv. So if mass is large, okay, if mass is large, then the wavelength will also be very large. Okay. Now due to that reason, what you will see that, okay, due to the weight of the, say, this thing, the wavelength associated with the ordinary object are too short to be detected. Okay, because ordinary objects have high mass, whereas the subatomic particles have very low mass, and therefore they are being detected by the what? They are being they are being detected by the wave nature. Okay, means they show wave nature. So subatomic particle like electron, okay, proton and neutron, they all can be experimentally detected due to their small masses. Okay, clear? Now we can conclude that all the electromagnetic radiation that we have, they all exhibit wave and particle nature. Clear? Now let us move to Heisenberg uncertainty principle. Now this Heisenberg uncertainty principle says that we cannot determine, means we cannot know the exact position and exact momentum. So what does this mean? So this term, you have heard it many times, but you should be very keen about what it is saying. So you know that if you talk about a car, suppose a car is moving. Okay, so I'm talking about macroscopic particle. Now if you calculate the position of that, and you know everything, that you can calculate the momentum, right? Then it is possible that we can know the position and momentum of particle, okay, of a particle that is subatomic in nature, sorry, that is macroscopic in nature, with the help of simple Newtonian mechanics. Okay, but if you talk about the electron, it is not possible, and it is quite strange also. Means you cannot apply the laws that you studied from the childhood about Newton laws and all to a particle. Okay, and only the Newtonian mechanics, not the, sorry, the quantum mechanics can only be applied to that particle and not the Newtonian mechanics. So that is something strange about this subatomic particle. Okay, so one more thing here. So we have seen earlier that, okay, the particle has both wave nature, sorry, matter has both wave nature and particle nature. So it is true for every object. So whether you talk about the subatomic particle or you talk about the macroscopic particle like table and chair, so they all have this wavelength associated with their movement. But since it has a very high mass, therefore the wavelength, okay, the wavelength has a very small length, right? The wavelength is very small, and therefore we cannot see the wavy pattern of the wave pattern of the macroscopic particle. Okay, so due to the high mass of that, we say that, okay, it is not practical to calculate the lambda of a heavy particle. Clear? Okay. Similarly, here also the uncertainty principle can also be not applied to microscopic particle, because of course there is uncertainty in their position and momentum, but that uncertainty is very small as compared to the measurements that we have taken. Okay, means we can ignore those measurements, or we can ignore those uncertainty. So here is our equation for that. So it says that the uncertainty in momentum and the uncertainty position, if you take the product of that, then we will get it as greater than or equal to h cut pi. So what does this mean here? Okay, means uncertainty means the certain means it is not able to we are not able to determine properly the amount of say, you can say, error in the position momentum, or you can say about the momentum operator. Now this uncertainty, or you cannot measure it, is always greater than or equals to h by 4 pi, but it is not less than h by 4 pi. Now if you just place p value here, that is m into v, then you will get lambda x is equals to delta m is x is equals to delta m, delta m vx, right? So this m is also a constant, that will give you delta x into delta v greater than or equal to h by 4 pi. Okay, so this is our final equation where delta x is uncertainty position and delta p x or v delta vx is the uncertainty in momentum. Clear? So what does this mean? That the delta x you are seeing here, it is the uncertainty in position. The delta p is the uncertainty in momentum, and delta vx is the uncertainty in velocity. Means you can say that we cannot know the position and velocity of a subatomic particle at the same time. We can go to more fundamental from momentum to this position, and we can tell this. Now, if the position of the electron is known with high degree of accuracy, so suppose if you are able to calculate the position of electron, and that also with high degree of accuracy means very precise to the accurate value, then you will see that the velocity will be very uncertain. Means this both of this goes complementary to each other. So if one is high, other will be low. If one is low, then other will be high. And this is very important because all of our say this delta x and delta, all of this are as a result of Hisenberg uncertainty principle. Similarly, if delta Vx is small, okay, if delta Vx is small, then the position of electron will be uncertain. Clear? Got it? Okay. Thus, we can carry out uncertain physical measurement on the electron position or electricity. The outcome will be depict a fuzzy or blur structure. Okay, so if we just do the same physical measurement on the electron, then the outcome will depict a fuzzy or blur picture. Now let us talk about the significance of uncertainty principle. So first of all, you must have seen in the Bohr's model that it says that the electron can move in a fixed state or a stationary state. So that thing was first illustrated by this thing. That is our uncertainty principle, because nothing is stationary here. There's always an uncertainty in that. Clear? The trajectory of a object is determined by its location and velocity of the at various moments. So if we know where a body is particularly at an instant, if we also know the velocity and the forces acting on it at that instant, we can tell where the body would be in some time later. So why is it important that we have to consider both the position and the momentum? So if we don't do so, so if the position and the momentum are both not the same, okay, means they're say if you know apart are not the same, then you cannot know the accurate value of that particle or accurate position of that particle. Clear? Okay. So this is our conclusion, that the position of a body and its velocity fix its trajectory. And since for a subatomic particle it is difficult to determine both of them simultaneously, therefore it is not able to track the electron. So it is talking about a tracking of trajectory of electron, and since it has this has no fixed position or fixed momentum, for that reason we cannot see it. So clear? Now this is the question. We have a question. So the question says that we will say that okay, this is not applicable for macroscopic particle, and the reason is this, that is given here. So if the uncertainty is applied to an object of mass, what should be a milligram? Say about a milligram. So what are we taking? We are taking the mass in milligram, and this is very large mass. Okay. If you put this value here, then you will get this uncertainty greater than, approximately equals to 10 to the power minus 28. Clear? So this is the uncertainty principle. So what we have taken, we are given the mass of the object, that is 10 to the power minus 6 kg, and with the help of that we have calculated h by 4 pi m. Clear? Now this value of delta V and delta X is extremely small. Therefore, one must say that in dealing with milligramized or heavy object, the associated uncertainty are hardly of any consequence. Say we have one more question here, which says that the uncertainty of only 10 to the power minus 8 meter is known for the position. So we can calculate what. So it therefore means that if one tries to find the exact location of the particle, say to an uncertainty of only 10 to the power minus 8, then the uncertainty is V is what, 10 to the power 4 seconds. Clear? So it is therefore means that the precise statement or the position and momentum have to be replaced by a statement of probability that the electron at a given pressure and position and momentum, okay, that the electron at a given position and momentum, this is what happened in the quantum mechanical model of atom. So here the question is that a microscope using suitable photons is employed to locate an electron in an atom within a distance of 0.1 angstrom. What is the uncertainty involved in the measurement of body? So this is the overall question. So what does it say? So it says that a microscopic using a single photon is employed to locate an electron which is at a distance of 0.1 angstrom. What is the uncertainty involved in the measurements of its velocity? So let's see. So delta x into delta p is h by 4 pi. If you put the value of p, m will be coming out. Okay, that will give you h by 4 pi. So v will be equals to h by 4 pi delta xm. Clear? Then delta v can be calculated as this value, 6.6 into 10 to the power minus 34 by 4.3 by 4 into 3 to 3.14 into 0.1 into 10 to the power minus 10 and 9.11 into 10 to the power minus 31. So if you just calculate this, you will get your value as 5.79 into 10 to the power minus 6. Sorry, 10 to the power 6. Next is a golf has a mass of 50 grams, right? A golf has a mass of 50 grams and a speed of 45 m meter per second. If the speed cannot be measured with an accuracy of 2%, calculate the uncertainty in position. So delta x we have to calculate. And delta p is not given and m we know. Okay, so we take first of all m here. Okay, so first we will take m. Then now we will move this mirror. So it has a mass of 40 gram and it has speed of 45 m meter per second. Okay, let's see the solution. So the uncertainty in speed will be 45 into 2 by 100. It is giving us 0.9. That is giving us delta S is equals to h by 4 pi mv 1.6 into 10 to the power minus 33. Clear? So it is clearly mentioned earlier also that large particle do not show what? Large particle do not show this uncertainty principle in a significant amount. So here are some reasons again given for the Bohr's model destruction. Okay, so first is an electron is regarded as a charged particle moving in a well-defined circular orbit. So it is not well defined, it will change. The wave nature of the electron is not considered in the Bohr model. And further, an orbit is an energy defined path and this path cannot be obtained cannot be completely defined only if both position and velocity of the electron are known. Clear? Now this is not possible according to Heisenberg principle and Bohr model of the hydrogen atom therefore not only ignore dual behavior of matter but also contradicts Heisenberg principle. Okay, because it is making us suitable to connect with both alpha particle and okay. So next. So this was for today's lecture. With this, I end my lecture. Thank you.